All right, we'll get started with blood banking reagents. And basically, the idea of this is to kind of get a lay of the land of what you're going to be responsible for using in the laboratory. So, I want to look at what monoclonal and polyclonal antibodies we're going to be utilizing within our reagents, what typical reagents we're going to do for our ABO front and reverse typing, what our RH typing we'll use, what do we use a control for, and what are we using for different reagent red blood cells. One of the things, this should be a reminder for you from immunology, and maybe you did, maybe you didn't utilize DAT testing, but your direct antiglobulin testing and your indirect antiglobulin testing, and which each of them are. I do have a quick short video that I utilize in my immunology course to be able to kind of give you a review of those procedures and give you a visual of what's happening inside the tube. Makes it a little easier to understand. So we'll go through and we'll look at the reagents that you utilize. So this is basically just an introduction. We'll start talking more specifically about this when we start getting into the actual workups as well. And then obviously looking at sources of error is always important. So, and again here, we'll also look at potentiating agents. So these are some of our things that we utilize to get the red cells closer to enhance agglutination. So low ionic strength solution, you've probably heard of it called LIS. Serum albumin made from bovine serum, PEG or your polyethylene glycol, and enzyme treatments. Be careful with enzyme treatments as it can change reactivity and that it can actually wipe out antigens off the top of the red cells. So you do have to be aware of these issues. And what are the lectins that we use within the blood banking technology, and then some of our automation gel technology or microplate techniques, and some of our solid phase capture. I have, as we get towards the end of this course, I have a lot of PowerPoints on the solid phase capture. We actually, when I was a supervisor, instituted this technology within the blood bank that I worked at and I ran. So we used solid phase capture, which was really cool and very fun to use. But typically we're going to see the gel technology being utilized. So when we look at blood banking reagents, there's four basic categories. So red cells with known antigens, and then antisera with known antibodies. So here you want to look at, and don't laugh, red shit and clear shit. And, not to joke around or be funny, and yes, I swore on a PowerPoint, but this actually really helps because what we're looking for is the opposite. So your red cells with known antigens. So these are reagent red cells, okay? Reagent red cells. And these reagent red cells have these known antigens, so we are going to actually compare our patient plasma. So here, to this, we're going to add patient plasma. And because here, if we have the red stuff, okay, what are we looking for? We're looking for antibodies, okay? We're looking for patient in the patient. So we're looking for patient antibodies. And I know my handwriting on this one, my Apple Pencil died, but I want to keep going and get you the stuff. So we're looking for the antibody in the patient. So if we're testing our patient sample with antisera with known antibodies, okay, what are we adding? We add patient RBCs. So we add a cell suspension, a drop of a cell suspension of the patient to look to see if they have any antibodies with any antigens on their red cells. Okay, so this would typically be our front typing, where we add our patient red cells to anti-A, anti-B, and anti-D to get our blood type. Then we have what's known as antiglobulin reagents. So these antiglobulin reagents are either our anti-IgG by themselves, our anti-complement, or our polyspecific AHG, okay, or our anti-human globulin in general. And that will actually have your IgG and your complement in it. And then potentiators to enhance antibodies are our fourth category, and these would be something to most commonly your LIS or your PEG. Some places use albumin, and then we can also look at spinning, pH, temperature, just to physically get them closer together, or change how they come together. So these are the typical ways, or are mechanically getting them together and adding potentiating agents to get the red cells closer, because the closer, so remember, you have each red cell, so this is a red cell, and they have their zeta potential in here. It's very hard for them to get close together. They're not designed to get close together. So what we need to do is minimize this gap here. So when we add things, okay, so then we add our potentiator, all right, we get our red cells a little closer together. Or we spin it, right, and then we spin it, and then we get that cell button where the cells are getting really close together. And then they agglutinate. So the actual agglutination is a lattice of that antibody bridging cells together. Okay, so this is your red cell, and this is your antibody. Okay, and remember, antibodies are not actually in this Y shape. They're actually in like a barrel form, and they trap the antigen inside that barrel. So it's actually really cool. Anyway, that was a tangent, but just in case you didn't remember. So one of the things that we have to be careful with our reagents is that they are actually regulated by the FDA, or the Food and Drug Administration. So we actually have to really look at, as supervisors, before we bring them in, we have to look at not only validation of these and actually looking at how they perform, but we have to look at the specificity. So are they recognizing the antigenic determinant and its corresponding antibody, and how strong the reaction is before they can actually license them? And we also have to look at this when we choose them to bring them into the blood bank. One of the things that we have to do, don't ever skip this, this is like blood banking 101, is our QC. Because basically when we run our QC, this is determining whether our testing is legit. And remember, in blood bank, this is the easiest way to not make a mistake that could kill someone. You don't want to give someone off-type blood banking, blood units. Now, most of the computer systems nowadays have computer checks, or checks and balances, where you've got to stop. There's a hard stop. You can't go past it. You can't assign it. But the thing is, we still have to rely on our brains and our knowledge in downtimes, or in smaller hospital laboratories where they don't have a huge LIS. You don't know where you're going to end up working. You could work in a giant lab. So they have huge automation in their blood bank, and you're super busy, and that they have a huge laboratory information system, so the computer will do a lot for you. But you could also work in a small laboratory where you do everything manually. I work in two different types of laboratories right now, and one I have automation and one I do manual. And we do use the same computer system, so I'm a little spoiled there. But one of the things excuse me, that we put into place is our QC, because our QC will tell us, yes, the reagents are performing the way they are supposed to. So I want you to take a look at, in the video section within the module, labeled videos. Take a look. I gave you a video on how you do QC, and that's how we do it at both the places I work at right now. Um, so the QC program, or quality assurance program as well, will go over everything that's involved in blood bank testing. And that could be anywhere from the techs that are doing it, to the space, to the safety, to the suppliers, everything. But when we start looking at QC itself, we have to actually look at acceptable reagent performance statements, documentation of our reagent use, and corrective actions for lack of performance with them. One of the things that we also do is every time we get a new shipment, we look at the package insert. The package insert gives us our manufacturer's instructions. So we need to make sure that if we have procedures that are written to these package inserts, that we check to make sure modifications weren't made. For a lot of our antigen typing of the red cell units, when we're doing the other blood group systems, our other antigens, we're going to be probably following the manufacturer's inserts. Most places just have a package of those, or a binder of those that we follow. So, when we look at commercial antibody reagents, the first thing we'll talk is our polyclonal antibodies. So, these you probably learned in immunology, where they're made from different clones of B cells, and these are actually created from a hybridoma, utilizing mice to isolate specific B cells that will secrete specific antibodies. So then we will actually look at all the different clones, and then we'll have multiple antibodies as well. And you can see that over here where we have our polyclonal antibodies, where our monoclonal come from the hybridoma and have specific, only this one can make multiples. And these will recognize multiple epitopes, so it allows us a little more fluid testing. So an example here is an anti-human globulin, and this will actually bind to any human globulin. Surprise, surprise. Our monoclonal antibodies, here's our hybridoma technique, where we have single clones of B cells that will secrete the same antibody. In this hybridoma, we'll only recognize a single epitope. So we'll use these for our anti-A, some of our anti-sera, and anti-IgG. So it's only making a 1. So this is just a quick summary that compares the two. So monoclonal antibodies can be IgG or IgM, and polyclonals are often a mix of them. And they can identify multiple epitopes in a polyclonal, but only one particular epitope in a monoclonal. Think mono, 1. Mono, 1. And then poly is many. So our blood typing. So typically when we do a blood type, draw this fast before it disappears. This is our forward, this is our reverse, and then we have A, B, D, and then A cells and B cells. Okay, and then here we'll add, no, don't go away. All right, so here we'll add our anti-sera, and then this is going away and it's not staying. I wish it would stay. But we'll add for our front type, it includes our anti-A and anti-B. Okay, so anti-A and anti-B, and then we add patient cells. Okay, and then we look for agglutination. All right, if we find agglutination, that means that the anti-A found the corresponding antigen. Okay, so if that anti-A finds a corresponding antigen, that means the antibody has bound to a red cell. Okay, a little happy donut. So if that is bound to a red cell, what does that mean? That means on the red cell, that right there is the A antigen. So the patient is at least partly type A. Okay, if they find, we add the anti-B, and then the patient cells, and there's no agglutination, okay, that means the red cells did not find an antibody, and they did not bind. That means the patient is not type B. Okay, so these here can show you the reactions here. So this is the anti-A, remember the clear stuff. Okay, we're adding the clear stuff, then we're adding the patient's red stuff, and we're looking for agglutination. And then we can actually define the phenotype from that. So your anti-A is directed to A antigen. Your anti-B is directed to B antigen. So, typically speaking, we'll see around a 3 to a 4 plus reaction. We do it at immediate spin because they're usually IgM in nature, and they are monoclonal. But what ends up happening is that as we get older, our immune system gets older, so we don't work as well. So our immune system doesn't work as well, and what ends up happening is we slow down our production of antibodies, and we will see a decrease in our reactions as well, but typically only in our back typing. Our front types will typically have the 3 plus to 4 plus reaction, but our back type will start weakening as we get older. Um, and then we will also check for expected ABO antibodies. We'll show you that in the reverse type. Our D antigen typing is our looking for our Rh blood group system, but the D antigen is very immunogenic, so we can have really big reactions to that. So on this one, we'll actually use a commercial anti-D, and this will be combined with the patient and donor cells, so agglutination will indicate that the presence is there. So when we look at our D typing, we use commercially made anti-D. We'll combine it with the patient and donor red cells. If there's agglutination, we find the D antigen. If there isn't, then it isn't there. We will use a negative reagent control, and that will indicate a false positive result hasn't occurred. So typically speaking, we're going to use those with someone who's type AB pos, or appears as AB pos, or cord blood, just to make sure nothing's interfering. So we have two different types of anti-D reagent. We have our high protein. These will be polyclonal antibodies with bovine albumin. We can also see a lot of false positive agglutination here. Or our low protein reagents. These are typically used more often than the high protein reagents, where they have monoclonal IgM antibodies or polyclonal blends with a smaller amount of albumin, and less false positive reactions. So our low protein reagent control will basically help us ensure that we're not getting any false positive results. So typically we can see these with protein abnormalities or cold autoantibodies. So if we get a patient that types up as AB pos, or it's a cord blood, we're going to want to run that control just to make sure, because we don't know if something else is causing all the red cells to agglutinate. So reagent red cells, these have known antigens. These will confirm the presence of antibodies in the patient's serum or plasma. So procedures that use this are blood type serum testing, our screen tests, and our antibody identifications. So our A1 and B cells will combine with the patient's serum or plasma to determine the reverse grouping. And basically patients who have the antibody against the antigen of the ABO system that is lacking than their red cells. So I know I used on my example, I'm type A, okay? So I should not react with A cells because those are mine. I shouldn't be making an antibody against them, but I will be making an antibody against B cells. And then you can see AB type has no antibodies because they have both the A and B antigen. So our A1 and B cells, these are usually reagents are made from pools of donors to a 2 to 5% concentration for tube testing, and they're negative for our Rh antigens because if we used positive Rh antigens, then they would be interfered. So if they look weird, the cells are really dark, or they agglutinate in the vial themselves, or have hemolysis, we don't want to use them. They're going to indicate a bad reagent. Our screen cells, we use these in antibody screen or antibody detection. And we're looking for unexpected antibodies. So typically there are 2 or 3 vials within each set. And they can either have a single or 2 donors that are pooled together. So typically speaking, we're not using pooled testing. We only use those for donor testing. We're not going to use those for a patient who's just about to get a transfusion because the single cell donors tend to give a stronger reaction. So screen cells will come with an antigram. So this is that antigram I was telling you about. So this is basically indicating, this plus sign here is indicating that the D antigen is positive on cell 1. And this is the Rh phenotype of that cell. So basically what we want to do is make sure that this antigram has all of the antigens that are clinically significant so we can rule them in or out. So these are what's regulated by the FDA, and this plus indicates it's on there, the 0 indicates it's not there. So our panel cells are the same as the screen cell, except they're usually either 10 to 16 or 11 to 16 cell panels, and they look the antigram looks just like the screen antigram, just with more cells. So basically, the procedure that we utilize for these is called the antiglobulin test. So this is basically where we have commercial antibody against a human globulin, and this will be used to agglutinate antibody-coated red cells. So what we're really looking for in our antiglobulin testing is the coating of the red cells of antibody. So reagent that contains antibodies towards IgG and or complement is typically used. So our DAT, or our direct antiglobulin test, will look for IgG or complement binding to the red cells in vivo or in the body. So what will happen is we'll wash our cells to make sure we don't have anything junky. So we'll wash that patient sample, and then we'll add our anti-IgG. So in this case, if we're doing a polyspecific DAT, we will add an anti-human globulin, which contains a polyspecific blend of anti-IgG and anti-complement. And if that is positive and we see this lattice formation or this agglutination, we need to do a differential DAT, which means doing the same procedure again, but with just the IgG separate, and then doing that same procedure again for the complement to be sure which one it is. Is it IgG in nature or complement in nature that's coding in vivo? Typically speaking, we'll do a DAT on a patient who's suspecting that they're having a transfusion reaction or like a hemolytic anemia. We'll do a DAT just IgG in nature for most newborns because we're not looking at complement at this point.
And we'll always use check cells in the end, and those are IgG coded red cells that will add to the tube, basically looking to see if you added the IgG reagent. It's just checking. So a positive DAT, we kind of already talked about this briefly, but the last one I didn't mention was it can be drug related. We can actually see IgG drug complexes attaching to cells that will form immune complexes. The indirect antiglobulin test, and this basically looks for IgG or complement in vitro. So we're making this happen in the tube. So this is our typical antibody screen or our antibody panel. That's the indirect antiglobulin test. So basically what we're going to do is we're going to take the reagent red cells. So we'll just do first an antibody screen at this point. So an antibody screen, so reagent cell 1, reagent cell 2, reagent cell 3 in 3 separate tubes or 3 separate gel wells. And we will add patient plasma or serum to it. Mix it up, let it incubate at 37 degrees Celsius. Then we wash it, and then we add IgG, and then we look for agglutination. If agglutination is present, that means there is some sort of clinically significant antibody present within the sample. And we'll have to further identify that by doing an antibody screen. Antibody identification. So we talked about the antibody screen where it looks for antibodies to red cell antigen. The antibody identification will specify the red cell antibodies. The cross match will determine compatibility between our donor and our patient. And then we have this one last test that we didn't talk about yet, which is our antigen typing. And this antigen typing is basically we're looking for a specific red cell antigen in a patient or donor. So we will antigen type a patient if we suspect that they have a certain antibody. We will antigen type them specifically for that antibody because we expect them to be negative, because we expect them to not form an antibody on something that they have. And then we'll antigen type a donor. For example, if a patient is identified with an anti-big K, we're going to antigen type the donor for the big K antigen because we want them to be negative, because we don't want to transfuse a patient with something that they react to. So what kind of sources of error can we see? Well, they're agglutinated before we've washed it. So this could be like a cold antibody. If we're using dirty glass, because we'll get junky in it. If they are not centrifuged right, over centrifugation can cause a red cell button that doesn't come off the bottom of the tube, and that can be considered a false positive. Other things, we don't wash right, or we don't do the test right away, or we don't identify a weak positive reaction, or the reagent is getting older or hasn't been stored well or is contaminated. We didn't add our anti-human globulin reagent. That's why we use check cells to make sure that we do. And then again, we maybe didn't centrifuge it, so then it looks negative when we didn't even give it a chance to agglutinate yet. And then we didn't make a cell concentration that's right, so it is not being tested in the zone of equivalence. So our cell suspension is too heavy or too light. So things like that. Our antiglobulin reagents, we briefly talked about this already, but we have our polyspecific AHG and our monospecific AHG. So the polyspecific has your anti-IgG and anti-complement antibodies. We'll get these from polyclonal or monoclonal sources. So agglutination will indicate that either or is coding the red cells, so IgG or complement. So then we need to do a differential DAT. So a differential DAT utilizes a monospecific AHG. So we will test the IgG, anti-IgG, and anti-complement separately. So they'll have an anti IgG reagent and an anti-C3b C3d reagent that will test to determine what is binding. So IgG will combine with the human gamma chains, and the complement will actually detect our complement proteins. And this will actually be looking for intravascular and extravascular hemolysis. So IgG sensitized cells, or IgG coated cells, or our Coombs control, if you some people call. These are required by the American Association of Blood Bankers as a control system when we're using AHG reagent and our results are negative. We have to add these check cells, and then we add a drop to the tube and then centrifuge it and look for agglutination, because agglutination here confirms the negative reaction. So we will do IgG sensitized cells with anti-IgG or anti-AHG. And false negative results within this are we didn't add the AHG reagent to begin with, the AHG isn't working right, or we didn't wash the red cells correctly. We also have complement coded red cells too, to confirm your anti-C3b, anti-C3d reagent addition in the same way as our Coombs control or our IgG coded cells. We have different potentiators, so our LIS will increase our antibody uptake, make that it'll enhance the reaction. Our PEG or our polyethylene glycol will concentrate the antibody test. Our enzymes will actually remove negative charges. We have to be careful though, because it does get rid of some red cell antigen. So it gets the cells closer, but it also wipes out some of the antigens. And then we can use albumin. The cells won't repulse each other, but we still have an extended incubation time. So we're looking at with 15 minutes with LIS, but a half hour with albumin. So our albumin is usually 22 to 30%, and they can get closer together than with saline. We like it likes direct agglutination with Rh antibodies, and it will enhance the sensitivity. But again, still a half-hour incubation. Our lectins, we have different types of things called lectins. These are actually seed extracts, and they actually have specificity towards red cell antigen. Imagine being the person that discovered that. Right? Just playing around with plants and you find out like we have some sort of blood bank application. Who knew? But these will bind to the carbohydrate determinants of the red cell antigens, so we can actually use these. Um, Other things that we can see, this gel technology is our dextran acrylamide gel, and it'll trap the agglutinated cells. So here is a negative reaction because the cells traveled all the way down, unimpeded by this gel. But here you can see a couple random cells here as a 1 plus, and then here some of the stuff has been trapped, lots of stuff trapped, ton trapped, and then here's a mixed filled reaction where we've got either a dual population of antibody or some sort of problem with that testing. Other things, we can do microtiter plates, same principle as tube reactions, where negative, where we'll see a smooth suspension of the cells, and a positive is a cell button. Our solid phase capture, this is a little funky because we have immobilized reagents. So cell that adhere to the sides indicates a positive reaction, but a negative reaction, if I can draw my tube does not want to draw, so we'll do it over here. A negative reaction will have a cell button on the bottom. Okay? So these are our reagents and methods in a nutshell. We'll talk way more about these as we delve more into the blood banking, but this is basically your introduction. All right.